So now that we've established what a game tree is, we're going to talk about how do you actually use a game tree to figure out what your right move is in any given situation, okay? And that's using a process called backward induction. Okay, so that's what we're going to look at today, backward induction and subgame perfect equilibrium. So backward induction is a method used to solve games where basically you start at the end of the game and you work your way backwards to the beginning to figure out a player's most rational moves. Okay, so one of the concepts in game theory is that you always assume that your opponent is smart and that they will always make the best move for themselves. Okay, so those are kind of like just the basic assumptions that you make. And these are the assumptions that you make anytime that you're in competition with somebody, right? You always assume that they're going to do something that's smart for them. So we're always going to assume that. And using that, you can make some guesses about what they're going to do and then decide what you should do and as a result, okay? So a solution when you use backward induction, the solution that you find is called a subgame perfect equilibrium, or sometimes it's called a rollback equilibrium. So let's look at this example. We got two countries that are on the brink of war. So player 1 and player 2 in this case are the two different countries. We just refer to them as P1 and P2 just for ease of talking about it. So the first country either accepts the status quo as it is, or they can threaten the other country. Okay, if that player chooses to threaten, right, so if he chooses to threaten, then player 2 has to decide that they're either going to back down in the face of the threat or they're going to escalate the conflict. And if that player chooses to escalate, then back to player 1, they have to choose whether they're going to back down from their original threat or if they want to actually go to war. Okay, so this is a table that represents that, right? Player 1 is where we start with the first choice of either accepting or threatening, right? So we can see this kind of broke down, right? Player 1 has to choose to either accept the status quo or threaten, right? If they accept, nothing changes, so we got these zeros as our outcome. If they make the threat and then the other country concedes to the threat, then player 1 gets a positive outcome, player 2 gets a negative outcome, right? Because positive for player 1, they've made a threat, they've improved their situation. Negative for the second player because they've backed down now and they're losing face, and they're probably also going to have to make some like accommodations for whatever the other country wants, so they get a negative outcome. Okay, if player 1 threatens and player 2 chooses to escalate the conflict, then player 1 is either going to go to war or back down. If they back down, then player 1, right, because player 1 is the one backing down here. So player 1 ends up losing out, so they get a negative outcome, whereas player 2 would get the positive outcome, right? If they choose to go to war, everybody gets a negative outcome. All right, so we got kind of this setup and we have these different outcomes. And again, the numbers here are just assigned by, it's really assigned by the players. It depends on what you find valuable and what you find less valuable. So as we kind of go through this, what you're going to do basically is you're going to say, let's start at the end and work our way backwards. So we're going to start at the end of this train of thought and work back. So assuming that all this stuff has happened, we get to this last choice node. Player 1 has to decide between these two things. Okay, so here's the part where you assume that both opponents are going to play rationally. So looking at this, right now, player 1, depending on what they choose, they have two different outcomes. Their outcomes are either going to be this -1 here, right, or this -2 here. Those are the two possible outcomes right now for player 1. So thinking logically is when you say, okay, well, based on these two different things, player 1 is either going to get an outcome of -1 or an outcome of -2. Well, neither of those are great, but -1's better than -2. So if I get to a point in my game where player 1 is in this position, they're going to choose to go to war because that's better for them than backing down. Okay, so I'm going to then say, all right, we're going to eliminate this as a possibility because once we get here, I know that player 1 is never going to choose to do this. They're always going to choose war over backing down because that will be a better outcome for them. All right, so now we're going to go back to player 2. So player 2, when they're choosing here to either escalate or concede, right? If they concede, then player 2, I know, is going to have an outcome of -2. All right, if they choose to escalate, before there were two possible outcomes that player 2 could have, right? But remember, we're assuming that player 1 is smart and is going to do what's best for them. So we're assuming that player 1's not going to back down because that would be a worse outcome for them. So player 2 can then assume that if they choose to escalate, player 1 will take them to war, in which case the outcome will be -1 for player 2. So now player 2's choice, if they concede, they get an outcome of -2. If they escalate, they get an outcome of -1. So similarly, player 2, it should never choose to concede because that's not going to give them the best outcome. All right, and now we back up another row. So now we're at player 1 again, and player 1 has to choose to either make a threat or just accept the status quo. So again, I'm kind of looking through this and I'm saying, okay, I'm looking at player 1 here. What are their outcomes? Well, if they choose to make a threat, we've already eliminated both of these as possible paths because they were not logical at other steps in the game. So if player 1 chooses to threaten, their outcome will be this -1 down here. If they choose to accept the status quo, then their outcome will be that +0. Well, not positive, just 0 up there, right? So from there, we can say, all right, well, given that option of either threatening or accepting the status quo, threatening is a worse outcome for the person making this decision. So they should choose to accept the status quo, right? This would be our ultimate outcome, which we would call a subgame perfect equilibrium. So our subgame perfect equilibrium, sorry, I spelled that kind of wrong, right? Is that on this first move, player 1 would just choose to accept the status quo and maintain things the way they are. Okay, now for a variety of reasons, people might not always choose that, depending on what the conflict is when you're actually talking about wars between countries. Again, these numbers might be different. Maybe going to war, right, would be a better outcome for you than accepting the status quo. So maybe these wouldn't be -1s compared to these 0s. So depending on how the players actually assign these numbers based on what's going on, things could change. All right, but that's how you do a subgame perfect equilibrium. So let's take a look at tic-tac-toe, okay? You instinctively know how tic-tac-toe plays. I'm going to assume that you know how to play this game. So what we have here is a partially completed game, just because finishing a full game would take so long to actually map out all the outcomes. You could do it, but it would just be huge. So we're restricting this a little bit. So basically we're at this point in the game, all right? And we are assuming that player 2 just made their move. So player 2's just made a move. And now it's player 1 turn, and they get to decide what their move is going to be. So this board right here is just literally copy and pasted for all of these. These are all the same board. So what are player 1's options? So player 1, let's see, player 2 is O's, so player 1 has to be X's. All right, so what are the options? They have 3 different things that they could do. They could place their X here, they could place their X here, or they could place their X here. Now, because you've probably played tic-tac-toe before, I'm pretty sure you have a feeling about which one of these would be the best option, all right? But the logic that you go through to figure out which one's the best option is the exact logic that we're going to do by making this game tree, okay? So that's why I wanted to do this one. It's a great illustration of what happens when you make a game tree and how, like, this is really practical for real life. Like, this is things that people actually do in their lives. So looking at this, right? So say player 1 makes the choice to put their X here. So now we're at a spot where we've got a new node here, and this is going to be player 2's choice. And they have 2 options for where they're going to place their X. So I'm going to make 2 different breakoffs. I'm going to recopy this tic-tac-toe board exactly the way it is for right now. So just recopying this, including our move that player 1 made. All right, so that's our same board. So now from here, player 2 has a choice to make. They can place their O either here or here. Okay, so now we're going to keep going. And I know that from here, like, you're looking at this and you're like, okay, so obviously we know then what the conclusion is going to be, right? Because from here, we only have one option left. There's only one spot left for player 1 to go. But to complete our game tree, we are going to make a new decision node for player 1. There's only going to be one branch off coming from this one, though, because there's only one place that they can go, right? So that would put player 1's X here. All right, similarly from this one, we're going to have our new decision node with our player 1 label, right? Here's my new board, or the board that was there to begin with, excuse me. And then our new move is going here. Okay, so looking at each of these, right, before we kind of finish the rest of this, next thing that I want to do here is I want to assign some point values. So it says in this problem that players earn a point for a win, they lose a point for a loss, and 0 points for a tie. So let's look at this board. And again, assuming that you know how tic-tac-toe wins, right? When you look at the results here, this is a tie. Nobody won, right? So player 1 would get 0, and player 2 would also get 0. That would be the outcome of this particular board. This one right here, player 1 has 1, right? We've got those 3 X's in the middle. So player 1 would get a point, and player 2 would lose a point. Sorry, I didn't mean to write parentheses there. It's just kind of instinctive because I'm used to writing points with parentheses. All right, so those are our 2 possible outcomes. Now we need to go back and finish our game tree. So other option, right? If player 1 had chosen to put their X here, then player 2 has a decision to make, right? I'm going to recopy this board exactly the way it is, including our new X for both of these. Okay, so player 2 now is placing their O, and their choices are to either put it here or to put it there. All right, if player 2 chooses to place their O there, we're actually done because at this point they've won the game, right? So at this point you would stop playing. You wouldn't actually bother to put another mark here because victory has been achieved. So that one's all set. This one over here, we don't have any victory yet, so we would need to have another one where, again, player 1's making a decision to place their last marker. So there's the board as it stands, and then player 1 would choose to put their X here, and that would cause them to win the game, right? So there's our win there, and on this one it was there. Okay, so what are our outcomes here? So in this case, player 2, who has the O's, won, right? So player 2 won, and player 1 lost. So -1, +1. All right, this one down here, player 1 was the winner, so they get 1 point, and player 2 loses a point. All right, last possible one. So from here, again, player 2, decision node. And I'm going to start by copying my board as is with our new marker. Speaking of markers, this one is dying. Okay, so in this case, player 2 has 2 choices where they're going to put their O. They can either put it here or they can put it here, right? If they put it there, then they've won, right? So the outcome is that player 1 lost and player 2 won. Okay, here we don't have a winner yet, so we would need to make a decision node for player 1, and then off of this, right, we have our same board, and they would put their X here, in which case it's a tie, right? So no one won and no one lost here. It just ends up being a tie. Okay, so here's our game tree. Excellent. So now, right, using our backwards induction, we're going to figure out what should player 1 do, right? So we have this original game here, right? But player 2 has already played, so he doesn't have a decision to make right now. Player 1 has a decision to make. So as they're choosing what they're going to do, we're going to use backward induction to figure out, well, which of these 3 moves should they make? Okay, so we're going to start at the end and work our way backwards. So basically, we're going to look at each of these little subsections down here and figure out what's the best option of the ones that we have. Okay, because if player 1 chooses to go this route, they're going to get one of these 2 outcomes. So for player 1, which would be the better okay, sorry. Nope, sorry. So if we're here, right, we've got to make this decision. Player 1, we're at player 2 right now. So if player 1 does this, player 2 is going to make a move. And if player 2 does either of these 2 things, we have to follow this. You don't really need to worry about what player 1 would do because once player 1 is here, they're forced into their next move, right? The last move is forced. So there's not really a decision there. The first decision, or the most recent decision, is for player 2. They have to choose one of these 2 things. So what I want to do is I want to compare, well, what are player 2's outcomes? If player 2 chooses to put their O here, they're going to walk away with 0. And if they choose to put their O here, they're going to walk away with -1. So when player 2 is presented with these game boards, which one of these 2 things would they choose? Well, they're not going to choose to do this, right? Because then they know that they're going to end up having a worse outcome. And obviously, right? Because then you clearly can see the other player is going to put next there and win, right? So from there, we can say, all right, I'm going to now then eliminate this as one of my possible paths because given the outcomes available, player 2 would not choose to do that. Okay, so now player 1 knows, well, if I do this, this is going to be the outcome. All right, so let's take a look at this next one. So in this middle section, player 2 is making a choice here. If they choose to go this way, then their outcome is going to be this positive 1. If they choose to go this way, player 1 has a forced move, right? And the outcome for player 2 will be negative 1. So which one of these two options should player 2 choose if put in this position? Clearly this one, because they end up winning there, right? So given these two options, this is better than losing. So they would eliminate this option. All right, last one. Again, player 1 just has a forced move here, so we don't really bother looking at it. But player 2 actually has two choices. If they choose to go this way, then their outcome is going to be this positive 1. If they choose to put their O there, then their outcome will be this at 0. So given the choice between those, they would again choose to eliminate this one, because that's going to give them the lower outcome. Okay, so now that we've trimmed this down, our actual question of what player 1 should do, player 1 now knows, okay, when I go to place my move, if I put my X here, then logically I know player 2 is not going to do this. That's going to lead me down this path. So if I place my X here, player 1 can say, I'm going to end up with an outcome of 0. Player 1 can say, if I place my X here, well, again, logically, player 2 is not going to do this, so I'm going to end up with negative 1. All right, and if I place my X here, then again, logically, player 2 is not going to do this, so I'm going to end up on this track with negative 1. So when player 1 is making their decision of which of these three things they ought to do, well, their options are 0, negative 1, or negative 1, right? You take the tie. It's better than losing, right? So from there, we would say, okay, player 1 is going to eliminate these as options, and this is going to be our subgame perfect equilibria. So our subgame perfect equilibrium is going to be that player 1 is going to choose to put their X here, and then player 2 will choose to put their O there, and then player 1 will be forced really to put their X there, and the outcome will be a draw game. Okay, and that should make sense to you because you understand how tic-tac-toe works, right? That is probably the decision that you would have made in the same position, right? You would kind of look at this and say, okay, if I put my X here, they're going to win. If I put my X here, they're going to win. So, oh yeah, I should put my X here and then nobody wins, right? Or you hope that maybe they'll do a stupid thing and you'll get to win, right? But if you assume that they're going to play logically, you just kind of look at this and go, oh yeah, it's a tie game, right? All right, one more. So this one's about a shared garden. So 3 people are planning to take care of a common garden, and they can each choose to either contribute or not contribute to make the garden more beautiful. So ideally, each person doesn't want to actually contribute, because if you have to contribute, then that's like time, effort, money, right? So they don't actually want to contribute, but they do want the place to look nice. For them, making it look nice means that at least 2 people are going to be contributing, because if only one person's contributing, that's kind of a weak garden. But if 2 people are contributing, it's going to be a little bit nicer. Okay. A similar concept to this would be 3 roommates trying to keep the place clean, right? Nobody wants to actually do the cleaning, but they would prefer to live in a clean place. So if only one person's doing any cleaning, the place is going to be gross, right? But if at least 2 people are cleaning, then it's kind of livable, right? So sort of the same idea. So you got these 3 people and they're making these choices in concession. So succession, excuse me. Player 1 has to choose to either contribute or not, right? And then based off of their decision, player 2 is going to choose to either contribute or not. And then player 3, based on that decision, is going to decide to either contribute or not. And you'll notice that now we have 3 different numbers listed at each outcome. So player 1's outcome would be these first numbers. The second number would be the player 2 outcome, and the third one would be the player 3 outcome. Okay, so that's not terribly different. It's a little bit different. So how are we going to do this? Well, we start by looking at the last decision that's made. So player 3 is making a decision, and based on where they end up, they're going to choose what they want to do. Okay, so for player 3, which we're adding a new color this time, yellow. So player 3, if they end up in this position and they choose to contribute, then this will be their outcome. Okay, if they choose not to contribute, then their outcome is 4. We were going to have a new color highlighter, but then that one didn't work. Let's try orange, see if this one works. This one works. All right, so those are our 2 possible outcomes in this position. So if player 3 ends up in this spot here and they have to make that choice between those 2 things, Clearly, they're going to choose to not contribute because that gives them the best outcome, right? So we can eliminate this as a path. All right, if player 3 ends up at this decision node, so we're focusing on this one here, and they choose to either contribute or not, then their outcomes will be either 3 or 4. So would they choose to contribute or not contribute? Well, in this case, they should choose to contribute, and we would eliminate this as an option. All right, if player 3 ends up at this decision node, then their outcomes would be 3 or 2. And given the option, they would prefer the 3. So they're going to choose not to contribute, or they're going to choose to contribute. All right, and then this last node down here, if player 3 ends up in this position, right, then you end up with a 1 or a 2. 2 is the better option, so they would choose not to contribute. All right, so now we've looked at all player 3 outcomes. Now we're going to go to the next decision node, which in this case is player 2's outcomes. So if player 2 ends up having to make this decision, they know that if they choose to contribute, player 3 is going to choose to not contribute. Because again, player 2 is assuming that player 3 is going to make the logical choice for them. So player 2 is saying, okay, well, if I choose to contribute, then my outcome will be this 3 here. But if I choose not to contribute, then I know that player 3 will choose to contribute, and this will be my outcome. So given the choice between the two, I would rather have the 4. So at this point, player 2 is going to eliminate this as an option. Okay, if player 2 ends up at this decision node down here, they know that if they choose to contribute, so will player 3, and they'll end up with 3. So, I'm sorry, they'll end up with, 3. It was 3, right? If they choose not to contribute, player 3 will also not contribute, and player 2 will end up with 2. So given those two things, which one would player 2 prefer? They want the 3. So they would eliminate this as an outcome. So now when we go back our next layer and player 1 has to make a decision, well, they can say, all right, if I choose to contribute, then I know that player 2 is going to choose not to contribute. And then I know that player 3 will choose to contribute. So I'm going to end up with an outcome of 3 here. If I choose not to contribute, then I know player 2 will contribute and player 3 will also contribute, and I will end up with 4. So based off of that, the best outcome for me is that I get this 4. So player 1 would then say, well, then I'm going to eliminate this path. And our subgame perfect equilibrium is that the first person is going to choose not to contribute, and the other 2 people will choose to contribute. And that sort of makes sense, right? If you have a sequential choice there where you're going to choose, then the other 2 people are going to choose, and you know that they would rather have a nice place than not a nice place, right? You can sort of like force that. This, by the way, is in no way me like saying that you should choose not to clean your apartment. You should choose to clean your apartment, like, because you know what's going to happen if player 1 is consistently choosing not to contribute and these guys are contributing, right? Nina and Talia are going to kick Emily out. All right, so Emily will be off finding her own new place to live. So you should always, when you're in an apartment situation, you should be contributing. Something like this works when it's a one-off, right? So this is the idea that you have this game that you're playing once, right? So if you're playing once, then you can get away with not contributing. But when you're in a spot where you're like doing this over and over and over again, where every single day or every single week, you have to choose whether you're going to contribute or not contribute to keeping your place clean, that becomes a different story, because now these guys are going to start saying, well, they never contribute. And if they're never going to contribute, then I'm not going to contribute either. And that's going to make some changes to our game. So again, I'm not saying that you should never clean your apartment and make your roommates do it. That's not going to work out well for you in the end. But this is how game theory works. And this is how you kind of can work back through a situation with multiple choices to figure out what is the best strategy that you could take.